Hello and welcome to another video with Leah. Today I'm going to be doing a chemistry final exam review. Topics included are going to range from dimensional analysis, SI unit conversions, titration, Lewis structures, resonance, acid and base, redox reactions, polarity, hybridization, molecular shapes, percent yield, stoichiometry, empirical formula, etc. I really hope you enjoy this video and find it helpful, and if you do, remember to subscribe and leave a comment down below. I'd like to know what you think. Now, as this is an exam review, I don't go into every topic in detail, so if you would like to know more about, let's say, resonance structures or empirical formula, I recommend that you go to my website and see the list with links to other videos in which I cover those topics. Convert 5067 micrometers to meters. So we are going to go from micrometers to meters. And to do that, well, let's start writing our equation. So all of this is going to be over 1, and we are going to convert this to meters, so we need to do the conversion factor. So we can say that micrometers are going to go on the bottom because we want them to cancel out, and meters are going to go on the top. Now, in 1 meter, there are 10 to the 9 micrometers. So now micrometers cancel out, and we are left with 5067 divided by 10 to the 9, and this will be meters. The answer is going to be 5.067 times 10 to the negative 6 meters. A box with a mass of 5.21 kilograms and a volume of 5.9 liters has a density of blank grams per milliliter. The first thing to notice about this problem is that we start off with kilograms and we end with grams, and that we start with liters and we end up with milliliters. So we need to convert these two units, the mass and the volume units. So we can start off by saying that this box has a mass of 5.21 kilograms, and we can convert this to grams. So I'll just put this over 1, because 5.21 over 1 is the same thing as 5.21. Now this is going to be converted to grams, so I'll put kilograms on the bottom to cancel it out, and grams on top. Now in 1 kilogram there are 10 to the 3 grams. And so this turns into 5,210 grams. The second part of this is to convert liters to milliliters. 5.9 liters over 1 is going to be multiplied by the conversion factor. The liters is going to go on the bottom because we want to cancel it out, and milliliters is going to go on top. So in 1 liter there are 10 to the 3 milliliters. So this is going to be 5,900 milliliters. Now density is equal to the mass over the volume. So we need to divide these two values. So the density in our case is going to be density equal to 5,210 grams, that's our mass, divided by the volume of 5,900 ml. Putting this into our calculator, we get 0.883 grams per milliliter. And this is rounded to 3 numbers after the decimal point. Iron has a density of 7.87 grams per centimeter cubed. A block of this element was placed into a beaker containing water. The initial volume read 5.5 ml, but after the block had settled into the beaker, the volume read 10 ml. How many grams was the block? This is another problem using the density equation. However, this time we want to find mass. And from the shortcut, we know that mass is going to be density times volume. Alright, so let's start this problem. So the density given is 7.87 grams per centimeter cubed. So the negative 3 just means this right here. The initial volume was 5.5 ml, so the volume started around here. Okay, and then the block settled into the beaker, and then we went to 10 ml. So this difference right here is going to be the block's volume. So what we need to do here is subtract and do 10 minus 5.5, which is equal to 4.5. And this will be in the unit of milliliters. So now that we have our density and we have our volume, we can calculate the number of grams. Now remember, 1 milliliter is equal to 1 centimeter cubed. And so we can go ahead and multiply these. We can convert this one to ml, or we can convert this one to centimeter cubed. Either one works. Alright, so we'll convert centimeter cubed to ml. So we're going to do 7.87 grams per milliliter and multiply this by the volume of 4.5 ml. And we'll just put that over 1 so we can see the fractions more clearly. Now in this equation, ml cancels out and we're left with grams, which is what we want because mass is counted in grams. Doing this multiplication, we get 35.42 grams, rounded to the nearest hundredth. A runner travels at 6.33 meters per minute. How many centimeters per second is this? Alright, so we need to convert meters to centimeters, and we also need to convert minutes to seconds. So 6.33 meters per minute. Well, we need to start writing our conversion. So let's convert the distance once first. So meters needs to cancel out, so we'll put that on the bottom, and we're going to go to centimeters. Now in 1 meter, we have 100 centimeters. Alright, so meters cancel out, and now we can convert our time. So we'll put minutes on the top because we need to cancel out the minutes here on the bottom. And we'll put seconds on the bottom here. So in 1 minute, there are 60 seconds. So now minutes cancel out, and we are left with centimeters per second, which is what we want, so we can go ahead and multiply. Now I would recommend in your calculator that you put these numbers in parentheses, alright, before dividing, so that your calculator doesn't get confused and give you a wrong answer. In the end, you get 10.55 centimeters per second. And just as a quick note, you can also write this as 10.55 centimeters per second and just write in -1 instead of putting a slot. These two mean the same thing. The isotope below is for the element blank, which has blank protons, blank electrons, and blank neutrons. Alright, so first we need to find the name of this element. So looking at the chemical symbol, we see Sn, and Sn is for tin. Alright, so looking on the periodic table, you can see that tin has 50 protons. That's its atomic number. Now, this is a neutral tin atom with no charge, and so the amount of positive must equal the amount of negative, so there will also be 50 electrons. So this is the number of protons. That is optional for them to write, but I'll add it here, now that we know it. Alright, and now we need to find the number of neutrons. Now recall that the mass number is equal to the number of protons plus neutrons. 119 is our mass number, and we have 50 protons. And now the missing information is the number of neutrons. And so to find that, right, all we need to do is subtract. So 119 minus 50 will give us our number of neutrons. Doing this subtraction, we get 69 neutrons. You're going to subtract the number of protons from the mass number to get the number of neutrons. Find the average atomic mass for an element based on 3 of its isotopes. Isotope A occurring at 52.4% with 208 atomic mass, isotope B occurring at 22.1% with 207 atomic mass, and isotope C occurring at 24.1% with atomic mass 206. To find the average atomic mass, we are going to be using this equation that goes like mass of isotope A times the percent divided by 100 plus the mass of isotope B times its percent divided by 100 plus the mass of isotope C times its percent divided by 100. And this will give us the average atomic mass. Now let's replace these masses with the ones given in the problem. So for A, it is 208. For B, it is 207. And for C, it is 206. This turns out to be 204.39. Here we have a chart that we need to complete. This is just practice on chemical names and chemical formulas. So in some we're given the chemical name, and in some we're given the chemical formula, and we need to find the other one. So for the first one, we have potassium carbonate. Now potassium carbonate is an ionic compound, and so we know that we are going to not use prefixes. Looking at potassium, it is symbolized by K, and carbonate is a polyatomic ion with formula CO3 minus 2. Potassium has a positive 1 ionic charge, and because this is an ionic compound, we need to make sure that potassium carbonate's formula is neutral. We need to find out how many potassiums and how many carbonates need to be combined so that the formula is neutral. Right now, if we add 1 potassium and we add 1 carbonate, we have a plus 1 minus 2 charge, which is a negative 1 charge, which is not 0. So what we need is a positive 2, so that it ends up 2 minus 2 is in fact 0. So we need 2 potassiums, so we'll symbolize that by a little subscript, and 1 carbonate. So this will be the formula for potassium carbonate. Let's do the next one. We are given the formula TiO, and we need to find its chemical name. Now Ti is titanium, and O is oxygen. Now we know the names of our 2 elements, and now we're going to look at what type of compound this is. Titanium is a metal, and oxygen is a nonmetal. Therefore, we know that this is an ionic compound. We also know that titanium is a transition metal, and so we will be using Roman numerals. The way we name these compounds is the full name of the first element, so titanium, and then the Roman numeral for its charge, and then the base name of the second element with the ending IDE. So instead of oxygen, we're going to have oxide. Now our next step is to write the charge in Roman numerals of the titanium ion. So in this case, we know that oxygen has a negative 2 charge, and we have some charge for titanium. Now in its entirety, we have titanium and oxygen as a neutral compound. There's no charge. So 2 plus something needs to equal 0. Now, negative 2 plus 2 is what will satisfy this, so we know that titanium has a plus 2 charge. Therefore, we put a Roman numeral of 2. Alright, so this is going to have the name of titanium 2 oxide. And if I can get this small enough, I can move it into here. Next, we have vanadium 3 fluoride. Now we know that vanadium has the chemical symbol V, and fluoride is the fluorine ion, which has chemical symbol F. The Roman numeral 3 tells us that vanadium has a plus 3 charge. Now we know that vanadium 3 fluoride is a neutral compound. So in total we have 0, and well, we know that there is a vanadium with a positive 3 charge, and we need to subtract something so that this is 0. We know that positive 3 minus 3 will be 0, and so we know that in total the charge coming from fluorines needs to be negative 3. However, we know that one fluorine has a negative 1 charge, and so we need 3 of these so that we get a negative 3 charge. Alright, so we have 1 vanadium and 3 fluorines as our chemical formula. Alright, so now we move on to some covalent compounds. The first one is triselenium heptoxide. Now with covalent compounds, we know that we're going to use prefixes, and that those prefixes are going to tell us the number of that element that is involved in that compound. So triselenium. Selenium is represented by the chemical symbol Se, and tri means 3. So we have 3 of these. So we'll write that as the little subscript. Now, heptoxide. Well, the oxide part is oxygen, which is O in the chemical symbol, and hept, well, that means 7. So we have 7 oxygens. So the chemical formula is Se3O7. These are quite friendly because they tell you right away how many of each element you have. Our next one is to write the chemical name of CO. C represents carbon, and O represents oxygen. Now, carbon and oxygen are both nonmetals, so we know that this is a covalent compound. And with covalent compounds, we use prefixes to indicate how many elements there are for that element. Now, in this formula, you see 1 carbon and 1 oxygen. Now, mono can never be used for the first element, so we're just going to leave that as carbon, not monocarbon. Now, for the second element, we use the prefix for 1, which is mono. Okay? And then we add the base name of the second element plus IDE, so monoxide. So carbon monoxide will be the chemical name for this. Next, we have ammonium nitride. Now, ammonium is a polyatomic ion with formula NH4 with a positive 1 charge. Nitride indicates the nitrogen ion that has a negative 3 charge. Now, in the end, ammonium nitride must equal a 0 charge, so it must be neutral. And so what we need to do here is have 3 ammoniums to cancel out the negative 3 charge of nitrogen. So with 3 positive 1s minus 3, this will equal 0, which is what we want. So the way we represent this is to write parentheses around it and then write our 3, and then we just have 1 nitrogen. So NH4, 3, N is going to be the chemical formula for ammonium nitride. Now our last one says Li2S. Li indicates lithium, and S represents sulfur. Now lithium has a +1 charge, and sulfur has a -2 charge. But we notice that lithium is a main group element. Therefore, we do not need to use Roman numerals. The only thing we need to do is exchange sulfur for sulfide. So instead of writing the ending as UR, we write the ending IDE. Now you will notice that the IDE ending is used for all of the second elements in all the ways we name things. So whether it's a covalent one or an ionic one with a transition metal or an ionic one with a main group metal. If there are 0.053 kilograms of ammonia, there are some number of atoms of hydrogen. Right now we need to go from kilograms of ammonia to moles of ammonia, and then to molecules of ammonia, and then to hydrogen atoms. Now ammonia is represented by NH3. Let's first convert kilograms to moles. Now to do that, we still need to go through grams. So 0.053 kilograms of ammonia, 2 grams of ammonia. Well, we know that in 1 kilogram there are going to be 10 to the 3 grams of it. Okay, and now we can convert to moles using the molar mass, so the weight of ammonia. So in 1 mole of ammonia, we have some number of grams. Now that weight will be the weight of 1 nitrogen plus the weight of 3 hydrogens. If you add those up, you should get 17.04 grams. So now grams of ammonia cancel out, and now we can go to molecules of ammonia. To do this, we're going to use Avogadro's number, which is 6.022 times 10 to the 23. So in 1 mole of ammonia, we have this Avogadro's number of molecules of ammonia. Okay, so now moles of ammonia will cancel out. And finally, we need to convert the molecules of ammonia to hydrogen atoms. So in this case, we're going to be using the ratio. So in 1 molecule of ammonia, just by reading its chemical formula, we know that we have 3 hydrogen atoms. Now knowing that, we're going to multiply. So this is all continued, all these multiplications. And finally, we're going to multiply this by, well, if we want to cancel out molecules, we'll put that on the bottom. So in 1 molecule of ammonia, we have 3 hydrogen atoms. Okay? And now molecules can cancel out. So make sure you put these numbers in parentheses, especially because we have exponents. When you do this calculation, it comes out to be 5.62 times 10 to the 24 atoms of hydrogen, rounded to the second number after the decimal point. So for these problems, I would recommend writing a map to keep track of where you are and where you need to go. Percent composition of hydrogen in valeric acid, which has a chemical formula of C5H10O2. Percent composition is given by this formula. So the number of atoms that we're looking at times that atomic mass of that element, all divided by the molar mass, and then multiplied by 100, so we can get a number that has a percent sign after. So percent composition for hydrogen is going to be how many atoms of hydrogen, that's 10, and then this is going to be times the atomic mass of hydrogen, which is 1.01, that's from the periodic table, divided by the molar mass. Now the molar mass for this compound is the weight of 5 carbons, 10 hydrogens, and 2 oxygens, and that will be equal to 102.15. Now we're going to multiply this by 100 to get a percent composition of hydrogen, and that will be 9.89%. There is a compound that has the following percent compositions by mass: 20.2% sodium, 37.26% sulfur, and 42.2% oxygen. Find the empirical formula. Now we know that the empirical formula is simply the compound written out with the simplest form of the subscript, so the smallest number of subscripts that we can have that still gives the correct ratio of those elements. Now to do this, we're going to start writing out what kind of elements we have. So we have sodium, we have sulfur, and we have oxygen. Now what I'm going to do is put the percent number over the atomic mass for that element. So for sodium, there is 20.2%, and I'm going to put that over its atomic mass of 23. Same thing for sulfur, so percent without the percent sign over its atomic mass, which is 32.06. And lastly, for oxygen, I will do the same thing, so percent over its atomic mass. Now we're going to do these divisions. So for the first one, it's going to be 20.2 divided by 23. And that's going to be 0.878. Next one is 37.26, all divided by 32.06. And this is 1.162. For this last one, we have 42.2 divided by 16. This is 2.638. Now, out of these three numbers that I just found, I'm going to divide all of them by the smallest number that we just found. So the smallest number of these circled numbers is the top one. They're all going to be divided by 0.878. Now we're going to do another division. Alright, so now we have three numbers, and usually these would be the subscripts. However, some numbers are not close enough for us to round. For instance, this one's fine. 1, it tells us straight away that we have 1 sodium atom. And here, 3.005, we can round that to 3. That's allowed. But for this one's very close to 1.33. And that's not enough to tell us whether it's 1 or it's 2. We need to multiply everything by 3. So all of this times 3 Okay, because if we have something that ends in 0.33 or something very close to it, we're going to multiply by 3. Alright, so now our numbers are closer to showing us what they actually are. So we have a combination of 3 sodiums, 4 sulfurs. This is very close to 4, right? And this one is very close to 9. And so we have 9 oxygens. So in the end, this is going to be the empirical formula for this problem. Na3S4O9. Now these are some acid and base questions, and they're fill in the blank. So first we have the Arrhenius definition. An Arrhenius acid increases the concentration of the blank ions in solution, while an Arrhenius base increases the concentration of the blank in a solution. An Arrhenius acid will increase the concentration of H+ ions, and an Arrhenius base will increase the concentration of OH, or hydroxide ions, in the solution. Now, next we have the Bronsted-Lowry definition. A Bronsted-Lowry acid, something protons, while a Bronsted-Lowry base, something protons. So from this, we know from our notes and our textbook that a Bronsted-Lowry acid is going to donate protons, and a Bronsted-Lowry base is going to accept them. You also might hear the phrase that a Bronsted-Lowry acid is a proton donor, and a Bronsted-Lowry base is a proton acceptor. Write the net ionic equation of the reaction between silver nitrate and sodium phosphate. Which are the spectator ions? Here we have the molecular formula with the reactants of silver nitrate and sodium phosphate written out, along with their products. This is a double displacement reaction, so these products were made by, well, the first one was made by combining the outer parts, and this sodium nitrate was made by combining these inner parts. Now we have this part, we're going to write the complete ionic equation, which means that the ones that are soluble, meaning the ones with the AQ next to them, are going to be broken up into ions. And the solid is just going to stay as its compound. So no breaking it up into ions. So for this first one, we have 3 silvers, each with a +1 charge. We are going to add that to 3 nitrates, each with a -1 charge. Going on to the next soluble compound, we have sodium phosphate, which breaks up into 3 sodium ions with a +1 charge each, added to 1 phosphate ion with a -3 charge. On the product side, we have this solid that's going to stay the same, and we're going to add that to this soluble compound written in ion form. So 3 sodiums, each with a +1 charge, added to 3 nitrates, each with a -1 charge. Now at this point, we have written our complete ionic equation, and the next step is to take out the spectator ions. Now spectator ions are the ones that look exactly the same on both sides. So let's just go through these polyatomic ions or elements and compare them to what we have on the right side. So for this first one, we have 3Ag+. On this side, it appears as Ag3PO4 combined with another thing. So this is not going to be a spectator ion because it looks different on both sides. Going on to nitrate, we have 3NO3- on the left side and on the right side. So we know that the nitrate ion is going to be a spectator ion. We will cross that out. Next, we have the sodium ion. This looks exactly the same on both sides. We have 3Na+ on both sides. This is another spectator ion. And phosphate, well, this appears as PO4 -3 on this side, but then it appears combined with silver on the right side. So phosphate will not be a spectator ion. Right now, the only spectator ions we have are the sodium ion and the nitrate ion. Now the net ionic equation is simply written without the spectator ion, so it's just whatever we have left. So what we did not cross out is the 3 silvers, each with a +1 charge, added to a phosphate ion to yield silver phosphate. Now a quick note here, the ions that are broken up from the aqueous or soluble compounds, those each have AQ next to them. I just didn't write it because it took up too much space. And also notice that when you have more than one element or polyatomic ion, it's going to be from a subscript to a coefficient. So in the complete ionic equation, you're going to write the subscripts that indicate the number of that element, If you have multiple polyatomic ions, such as 3NO3, right, you're going to write that 3 in the front. Alright, so this is the net ionic equation, and these are the spectator ions. When ammonium chloride reacts with barium hydroxide, what forms? In this question, we want to know the products. When ammonium chloride, we'll write out the chemical formula, and barium hydroxide react. Alright, so for this one, we're going to look at this chart, okay, and these are the reactants, so we're going to look at what is on the left side of these arrows and match it up. So first of all, we know that we have ammonium, and we know that this barium hydroxide is a strong base. The first one of these is a metal carbonate and an acid. These reactants we do not have. Next, we have a metal bicarbonate and an acid. Again, we don't have that. We have ammonium and a base. A metal sulfide and an acid, nope. Acid again, no. The last one is what we're going to go with. Right, we have a strong base, and we also have an ammonium salt. So this is an ammonium salt. Ammonium combined with a negative ion. Alright, so if we're going to go with this one, our products are going to be a metal salt along with ammonia and water. So the metal salt is going to be a combination of the metal and the anion from the other one. So barium chloride is going to be our salt, and we're going to add this to water and ammonia, which has NH3 as its chemical formula. Find the species that fits with these characteristics: oxidized, reduced, lost electrons, gained electrons, oxidizing agent, reducing agent. Now what we need to do to solve this question is to find the oxidation numbers for each of these elements on both the reactant and the product side. And to do this, we're going to use the oxidation number rules. We start out with aluminum just by itself, and that is going to have an oxidation number of 0. Next, we are going to go over to HNO3. Now we know that hydrogen has a +1 charge, and we know that oxygen has a -2 charge. However, there are 3 oxygens, so in total, the oxidation number coming from oxygens is -6, so -2 times 3. We can also total the hydrogen oxidation number, which is +1. Now, in total, HNO3 has a neutral charge, so something, right, needs to add up to equal 0. Right now we have this, and we need to add something, so it's 0. Now, right now we have -5 here, so a +5 would make this 0. So nitrogen has a +5 charge for its oxidation number. Next, we go on to KOH. Now we know hydrogen has a +1 charge. So on the bottom it's each, and on the top it's total. Right. Oxygen has a -2 charge. There's one of those, so the total coming from oxygen is -2. And we know that potassium is in group 1, which means it has an oxidation number of +1. Alright, now going on to the product side, we have KNO2. Now each oxygen is a -2 oxidation number. Now there are 2 of them, so it's -4 in total. Potassium again is in group 1. We know that it has a +1 oxidation number. Now KNO2 is neutral. So +1 minus 4 plus something else needs to equal 0. Right now we have -3 plus something equals 0, so that's going to be +3. So nitrogen here is +3 in total and each, because it's just one of them. Next we have KAlO2. So in this case, potassium is again +1, oxygen is -2, -4 in total because there are 2 oxygens, and we know that +1 minus 4 needs to equal 0. So aluminum needs to be +3. And finally, we have water, H2O. So each oxygen is -2. In total, that's -2 for oxygen. Hydrogen's oxidation number is +1 for each, but in total, because there's 2, it's +2. Now we need to look at where the oxidation numbers changed and for which species those were, and then we can assign these labels. So looking at this, we see that aluminum went from a 0 oxidation number to a +3 oxidation number. Okay, just comparing these. Okay, so aluminum had an increase of oxidation number. Let's see what else changed. Looking at this, we see that nitrogen went from a +5 oxidation number. Alright. And then on this side, it had a +3 oxidation number. So nitrogen's oxidation number decreased. So now we know which elements had an oxidation number change. We can begin to label them. So an increase of oxidation number indicates that that thing was oxidized. Alright, it lost electrons because it went more positive, so it had to lose the negative. And finally, we'll call this the reducing agent. Okay? If it was oxidized, then it had to be the opposite agent. So then we know that nitrogen is just the opposite. So if the oxidation number decreases, then that species was reduced, it gained electrons, and we call it the oxidizing agent. Now, in the end, for an exam, they're going to say that HNO3 and Al are the ones you need to look at, right? So they're going to say that aluminum by itself, okay, looking at this one, is the one that's oxidized, and that nitric acid is the one that was reduced. Okay, so they're looking at the entire compound and not just nitrogen. But we have to look at nitrogen separately so we can figure out that change in oxidation number. But in the end, the answer could be listed as just this, okay? So the whole thing. So aluminum is by itself anyway, but for nitric acid, that's combined, and that'll probably be how they show it. So for these redox reactions, you have to remember that the answer is going to be listed on the left side. Use the combustion reaction of propane, C3H8, for the next questions. Alright, so combustion means that we need to add this hydrocarbon to oxygen to produce water and carbon dioxide. Now I have a video on the reactants and the products of combustion reaction, so you can go ahead and take a look at that if you are unsure how this reaction was written. So the next step is to balance this equation. So I'll begin by adding a 3 right here. Now I have 3 carbons on the right side. Next we'll do hydrogen, so I'll put a 4 here. And we'll do oxygen last. So on the left side we have 2 oxygens, and on the right side we have 4 plus 6, so that's 10. So I'll respond by putting the 5 right here. Alright, so this is the balance reaction that we are going to be using for the next questions. There are 5.46 grams of oxygen gas. Find how many grams of carbon dioxide are produced. So this is a stoichiometry problem. It's about finding the relationship between the reactants and the products. So there are this many grams of oxygen, and we need to go to grams of carbon dioxide. So the math that we are going to be using is going to be grams to moles of one thing, and then from moles of that thing to moles of another thing, and finally to grams of that thing. Okay, so purple is one of the species and green is the other species. So in this case, purple is going to be the oxygen gas, and the right side, or the green, is going to be the carbon dioxide. Alright, so we see that we start off with grams of oxygen gas, 0.6 grams O2, right, and we need to convert this to moles of oxygen gas. And to convert from grams to moles, we need to use the molar mass. So canceling out grams, well, grams goes on the bottom and moles goes on the top. So in 1 mole of O2, we have 32 grams of O2. So grams cancel out. And next we need to go to moles of carbon dioxide. So we need to cancel out moles of oxygen gas. So that will go on the bottom. So we'll just put a note here. That's oxygen gas. And we're going to go to moles of carbon dioxide. Now, this relationship is going to be found by looking at the balanced equation. So when we have 5 moles of oxygen gas, we get 3 moles of carbon dioxide. So we're going to put a 3 here and a 5 here. And now moles of oxygen gas are going to cancel out. Next, we need to convert from moles of carbon dioxide to grams of carbon dioxide. So in 1 mole of carbon dioxide, we need to find the molar mass and then put the grams of carbon dioxide. So the molar mass of carbon dioxide is going to be equal to 12.01 plus 32, which is going to be 44.01. You're just adding the atomic masses for those elements. Now moles of carbon dioxide cancel out, and we are left with grams of it. So now we can just put this in our calculator and multiply the stuff on top and then divide by the stuff on the bottom. Doing this, we get 4.51 grams of CO2. There are 40 grams of oxygen and 61 grams of propane. There are blank grams of water made and an excess of the reactant called something. What is the limiting reactant? So in this problem, we're going to find which reactant, either propane or oxygen, gives the least amount of water. And whichever reactant that is will be called the limiting reactant. So for each one of these, oxygen and propane, we need to figure out how many moles of water are made, and then whichever one makes the least amount of moles, we can convert that moles of water to grams of water and answer this question. And then we're going to see which one was the excess reactant and which one was the limiting one. So first we need to see which of these makes the least amount of water. So what we're going to do first, we're going to do the oxygen. So we're going to do grams of oxygen to moles of oxygen to moles of water. To convert grams to moles of oxygen gas, we need to use the molar mass. So 32 grams. So 32 grams of O2 is in 1 mole of O2. Now grams of O2 cancel out. Now we're going to go ahead and convert this to moles of water. So moles of oxygen gas are going to go on the bottom and moles of water are going to go on the top. And this is going to be from the reaction. So looking at these two, for every 5 moles of oxygen gas, we have 4 moles of water. And now this cancels out. This is going to be equal to 1 mole of water. Alright, now let's see how much water we can make with 61 grams of propane. Alright, so for this, we need to convert these 61 grams of propane, 3H8, right, to moles of water. So similar process, we're going to look at this and go from grams of propane to moles of propane to moles of water. From grams to moles, we're going to use the molar mass. So the number of grams in 1 mole. And that's going to be the weight of 3 carbons plus the weight of 8 hydrogens. That's going to be 44.11 grams of propane for 1 mole of propane. Next, we need to go to moles of water. So to cancel out moles of propane, we'll put that on the bottom, and we'll put moles of water on top. We have to look at the balance equation to get this ratio. So for every 1, right, because there's nothing here, it's just a 1. So for every 1 mole of propane, we have 4 moles of water. So 4 moles of water to every 1 mole of propane. Mole of C3H8 cancels out, and now we can do a math. And this will be 5.53 moles of water. Alright, so now we need to compare. These are our 2 choices. Okay, we're either going to make 1 mole or 5.53 moles of water. So we're going to have to choose the lesser amount. And which one made the lesser amount? Well, that was oxygen gas. So oxygen gas will be the limiting reactant, and the one in excess is called propane, or C3H8. Now we need to find how many grams of water we made. And notice I didn't solve these 2 equations, 2 grams of water. because I didn't want to waste time finding the grams of water for one that we didn't want or need. Right, so in the end, I choose the one that made less water and convert this one to the number of grams of water. And we know that in 1 mole of water, we have 18.02 grams of it. Okay, so this is going to be the number of grams of water that we need. If 12.16 grams of glucose had an actual yield of 88.25%, how many grams of carbon dioxide were made? This is a percent yield problem. So what we're going to do for this problem is to find the theoretical yield and then multiply that theoretical yield by this percent so we can know how many grams that was. So first we're going to convert grams of glucose to moles of glucose, and then we're going to convert moles of glucose to moles of water, right? And then we're going to convert that to grams of water. And then after that, we're going to do the same thing, only for carbon dioxide. So let's do this first one. 12.16 grams of glucose. This is the C6H12O6 formula. That's going to be converted. Then we'll use the molar mass to find the number of moles of glucose. So the molar mass of glucose is going to be 6 times 12.01 for carbon plus 12 times 1.01 for hydrogen, and then finally plus 6 times 16 for oxygen. And that turns out to be 180.18 grams of glucose per 1 mole. So now glucose grams cancel out, and we're going to go to moles of water. When we have a mole-to-mole conversion, we need to use the balanced equation. So for every 1 mole of glucose, we produce 6 moles of water. Now moles of glucose go away. Finally, we're going to do this to convert to grams of water. And we're going to use this using the molar mass of water. So in 1 mole of water, we have 18.02 grams of it. Now this cancels out. Now we can find the number of grams of water that were made by multiplying straight across. For this first one, we come out to have 7.3 grams of water. However, in the question, they tell us that we only produced 88.25%. So what we need to do is multiply 7.3 times this percent. You can either do 88.25 over 100, or you can just go ahead and do 0.8825. And this is when you have already divided by 100. So then we're going to multiply this, and we get 6.44 grams of water. Okay, so this is what we actually produced, given the actual yield. Alright, so that's one of our answers. Let's do the same thing for carbon dioxide. Again, we start off with 12.16 grams of glucose. I'm just going to write gluc or glucose. And we're going to multiply this by the molar mass of glucose so that we can get the moles of glucose. So grams of glucose on the bottom and moles of glucose on the top. So in 1 mole of this we have 180.18, and now grams of glucose go away and we're left with moles of glucose, which need to be converted to moles of carbon dioxide. So moles of glucose will go on the bottom because that's what we want to cancel out, and moles of carbon dioxide will go on the top. Now, to do this mole-to-mole conversion, we need to look at the balanced equation, and it turns out that for every 1 mole of glucose, we have 6 moles of carbon dioxide. Okay, so we're going to cancel out the moles of glucose, and then we're going to convert to grams of carbon dioxide. So this is going to use the molar mass of carbon dioxide. So in 1 mole, of carbon dioxide, we're going to have a number of grams of carbon dioxide, 44.01 to be exact. Now, moles of carbon dioxide cancel out, and we can multiply straight across to get our number of grams of carbon dioxide, and this will be theoretical yield. We get 17.82 grams of carbon dioxide, but remember, we had an actual yield of 88.25%. We need to multiply this theoretical yield by the actual yield to get our actual number of grams. When you multiply these two numbers, you get 15.73 grams of carbon dioxide. Alright, so this is how much water you can make, and this is how much carbon dioxide you can make. A volume of 60 ml of 0.57 m solution of base was diluted to a concentration of 0.3 m. How much water was added? So this is a dilution problem. And remember, for this one, we use this equation, m1 times v1 is equal to m2 times v2. Initial concentration times initial volume should equal final concentration times final volume. 1 and 2 for initial and final, respectively. So first we had a volume of 60 ml and a concentration of 0.57 m. And this is going to equal the final concentration times the final volume. So was diluted to a concentration of 0.3 m, so the final concentration is 0.3. And we need to know how much water was added. Alright, so we don't know the final volume, so we'll just put V2 for now. Now let's solve for V2 first. So we're going to do this by dividing both sides by 0.3 so that it can cancel out on the right side. This gives a final volume of 114 ml. And this makes sense because we diluted it, meaning we should have ended up with more volume because we added water. That's what you do in a dilution. So we have this, let's say, beaker. First it was at 60 ml, and then we diluted it and it went up to 114 ml. So how much water was added? So that's going to be this difference in here. And this is 54 ml. So the first step here was to find the final volume, V2, and then to find the difference between the final and the initial volume, find how much water was added. There are 65.9 micrograms of nitric acid in a solution whose concentration is 0.0577 m. How many milliliters is the solution? This is about molarity. Now, molarity has this equation, m for molarity is equal to the number of moles divided by the number of liters. A shortcut is this here, so moles over molarity in liters. Okay, and I showed this in a previous video. So basically, the thing is that you cover the unit that you want, and you're left with some other two units, and those would either be multiplied if they're side by side, or divided if they're one on top of the other. So we have nitric acid. So nitric acid has the chemical formula of HNO3. We need to find how many milliliters this solution is. Milliliters is a unit of volume. So in the end, we're looking for something about volume, and before we get to milliliters, we'll have to do liters, because this molarity equation only deals with liters and not milliliters. So we're going to have some equation that looks like this, and we need to find the parts to it. Right now we have the concentration, okay, but we need to find the moles given this number of grams of this compound. So let's convert 65.9 micrograms of HNO3 to grams of HNO3 and then 2 moles of it. Alright, so the number of grams and the number of micrograms. We know in 1 gram there are 10 to the 9 micrograms. This is our conversion from micrograms to grams. And then we need to convert this number of grams to moles. The molar mass is the number of grams in 1 mole of this compound. That's going to be the mass from hydrogen, nitrogen, and 3 oxygens, which is going to be 63.02 grams in 1 mole. So now grams cancel out. We're left with moles. So now we can multiply. This ends up being 1.05 times 10 to the negative 9 moles of HNO3. So now we can place our moles on top and our concentration here, right? And that will give us our number of liters of HNO3. Number of liters will be the number of moles, so we can just drag that right here, divided by the molarity, 0.0577. Now, because we know that molarity is equal to moles over liters, we know that moles cancel out, leaving us with liters on top. This is going to be 1.82 times 10 to the negative 8 liters. Now we're going to have to convert this to ml. So let's just multiply this by 10 to the 3. The conversion factor looks like this, though. This is going to be giving 1.82 times 10 to the negative 5 ml. Find the concentration of a solution with a pH of 1.1. So concentration of hydronium ions, or H+, same thing, is going to be equal to 10 to the negative pH. Right, so what we need to do to find the concentration here is do 10 to the negative pH of 1.1. And this will give 7.94 times 10 to the negative 2. Next, we need to find the pH of a solution with a concentration equal to 0.002512. Now the pH is equal to the negative log of the concentration. So that will be HNO3 plus or H plus. So it's going to be the negative log of this concentration here, so 0.002512. This is equal to a pH of 2.6. This answer up here can also be written as 0.0794. Now comparing the pHs of 1.1 compared to 2.6, we know that a pH of 1.1 is going to be more acidic than a pH of 2.6. Just look at a pH scale. So as you go into higher pH values, you become more basic and less acidic, and as you go lower in pH values, you become more acidic and less basic. Find the concentration of HCl if 14.7 ml of it were needed for titrating 20 milliliters of 0.117 m of barium hydroxide. For this problem, for titration, we need to make sure that the number of moles of acid and base are fitting to their balanced equation. So HCl plus BaOH2, these two are added to make water, and the salt will balance this equation. Okay, so this is the reaction we're dealing with, an acid and a base added to titrate. And we need to notice this ratio. 2 moles of acid are needed for every 1 mole of base. In the end, we're going to have to find the concentration of HCl. So concentration, we're going to be using the molarity equation, which is equal to number of moles over liters. So for HCl, somehow we need to find liters and moles. We already have volume. We have it in milliliters, but we can easily convert this to liters. Now, to get the moles of HCl, we're going to have to use the base information to get them. Remember this shortcut? Well, we have volume and we have molarity. We have these two things, and we know that if we multiply them, we get moles. So let's go ahead and do that for the base. So for the base, okay, the number of moles of base, that's going to be equal to the volume times the molarity. So we have this, okay, times the volume. But because the molarity equation only deals with liters, we need to convert 20 milliliters to liters first. So we'll do this equation, ml, put it over 1, and then do the conversion, which is 10 to the 3 ml to every 1 liter. So ml cancels out. Right, and now we have this equation that we can solve to get the number of moles of base. We get 2.34 times 10 to the negative 3 moles of base. Now, like I said earlier, we need to pay attention to this ratio. Because if we have this many moles of base, well, we have twice as many moles of HCl. So this value needs to be multiplied by 2 so we can find our number of moles of acid. We could also do this equation where we say this many moles of base, well, we're going to multiply that by this ratio. So moles of base, 1 mole of base to every 2 moles of acid. Okay, and then moles of base will cancel out, BaOH2. And if we multiply this by 2, we get 4.68 times 10 to the negative 3 moles of acid, so HCl. So now we have our number of moles of acid. And we're almost there at completing this. What we need to do now is find the number of liters of acid that we have. So if you just divide this by 1,000, you'll get the number of liters. Okay, so in the end, the molarity or the concentration of HCl is going to be the number of moles, so 4.68 times 10 to the negative 3, whole divided by liters. So 0.0147 liters. This gives 0.318 for molarity of HCl. What is the frequency of a light with a wavelength of 650 nanometers? Alright, so now we need to call that the speed of light. Equation goes as wavelength times frequency, and we know that a shortcut is this. Works the same way as the one for molarity. You cover up the one that you want, and 2 things are going to be left, which you're going to either multiply or divide. Now, for this one, we want to find frequency, and frequency is represented by nu, that looks like this. The other one is called lambda and stands for wavelength. So frequency is equal to speed of light divided by wavelength. Now, the speed of light is a constant. It's a number that you should know, and it's going to be approximately 3 times 10 to the 8 meters per second. Then you have wavelength with 650 nanometers. Now, the thing wrong with this equation is that we cannot do math with different units. Okay? Either nanometers needs to be converted to meters, or meters needs to be converted to nanometers. So before we put this in, we need to convert this to meters. Okay, so we can say that in 1 meter we have 10 to the 9 nanometers. Okay, and that's going to be equal to 6.5 times 10 to the negative 7 meters. And now we can do our math. And meters cancel out. This gives 4.62 times 10 to the 14, and this will be the frequency. Find the energy per mole of a photon that has a frequency of 8.34 times 10 to the 11 hertz. A hertz is just a unit of frequency. So energy equations go like this. So energy can be Planck's constant times the frequency. You can also say energy is equal to Planck's constant times the speed of light, all divided by wavelength. Now, given frequency, we'll go ahead and use this one right here. Right, just be aware that this equation also exists. It means the same thing. Now, when it says energy per mole, we know that we're going to have to multiply our final answer by Avogadro's number. But first, let's just find the energy. So energy, Planck's constant, well, this is going to be equal to 6.63 times 10 to the negative 34 joules times seconds. And this will be multiplied by frequency of hertz. So 8.34 times 10 to the 11, and we'll just write this as cycles per second. And so seconds cancel out, and we're left with joules. So in the end, we get this many joules. Make sure that when you do this math, you put this in parentheses so that your exponents don't get messed up. Next, we're going to multiply this by Avogadro's number so we can get the energy per mole. And this is going to be equal to 333.02 joules per mole. How many orbitals are there for when the principal quantum number is 4, or n equals 4? For this, we need to remember our knowledge on quantum numbers. Right, so we have n equals 4. We need to find our L value, and we also need to find the m's value, and we need to find how many m's of L's values there are. And we know that L values are allowed to be 0 up to n minus 1. So they have a max of n minus 1. So in this case, it's going to be equal to 0, 1, 2, and 3. Okay, this is the max number because 4 minus 1 is just 3. Next, our nth of L values. These values are from negative L up to 0 and up to the positive form of L. And therefore this will be so negative 3, negative 2, negative 1, 0, 1, 2, and 3. Now, how many orbitals is this? Well, we just count them all. We have 7 orbitals. Okay, so the number of orbitals is the number of m sub L values. What is the shape of an orbital when n equals 1? Again, we're going to consider our quantum numbers. So in this case, L values are going to be 0 and just 0 because they can only go up to n minus 1. They cannot be n. Now there's this chart that has L values, so 0, 1, 2, and 3, and it corresponds it with letters, so S, E, D, and F. I would recommend that you know this chart, okay, know the order of these letters and these numbers, and which ones they correlate with. And we know that if L equals 0, we're dealing with an s orbital, and s orbitals are shaped as spheres. So when n equals 1, the shape of the orbital will be a sphere. So we need to convert to L values so that we can correspond it to this chart and then to the shape. An orbital has 2 electrons. One of the electrons has the following quantum numbers: n equals 3, L equals 1, m sub L equals negative 2, and m sub S equals positive 1/2. What are the 4 quantum numbers of the other electron in the orbital? Right, well, first of all, we know that in one orbital, like written in electron configuration, we know that a max of 2 electrons can fit. Okay, so they're just telling us that in this one we have one spinning up and one spinning up, and they just gave us the quantum numbers of the one pointing up because it is a positive 1/2. It's spin quantum number. So those were n equals 3, L equals 1, m sub L equals negative 2, and m sub S is equal to positive 1/2. That was the upward pointing electron. Now the downward one is exactly the same until the m sub S value. And because the other one is going to point down, we're just going to write the negative 1/2. So the 4 quantum numbers for the other electron are going to be n equals 3, L equals 1, m sub L equals negative 2, and m sub S equals negative 1/2. What is the electron and noble gas configuration of a sodium ion? Alright, so on my channel, I recently made a video on electron configuration and orbital diagrams for the first 20 elements. So you can go ahead and look at that for an extensive overview of the electron configuration and how we do that. But this one is just going to ask for a sodium ion, so we need to do Na+. That's what sodium ions usually look like. Okay, and we're going to write the electron and noble gas configuration. So let's start out with the electron configuration. So remember this triangle, so we go 1s, 2s, 2p, 3s, and 3p, and 3e. And we go on, but that's all I'm going to draw. So we go this one first, then we go with 2s, then we go 2p and 3s, and then we go 3p, and so on, and then 3p. Okay, and of course the values down here will affect what we go next before we can look around. Alright, so let's start doing this. So the electron configuration, well, we need to figure out how many electrons the sodium ion has. So sodium has 11 protons, and to be positively 1 charged, it needs to have 10 electrons, so 1 less negative than positive. To write 10 electrons, we're going to write 1s2, 2s2, 2p6, because the superscripts add up to 10, because we have 2 plus 2 is 4, plus 6 is 10. So this is the electron configuration for the Ne plus ion. Now we need to write the noble gas configuration. So that is just going to be writing in brackets the noble gas that came before sodium plus anything else that was not covered. So the noble gas that's before sodium is neon with 10 electrons. And now neon has 10 electrons, so all of this is taken care of. This goes right in here, written as neon in brackets, and there's nothing left over. So there's nothing after this. It's just Ne in brackets for the noble gas configuration. Describe the difference between 1. Ionization energy, and 2. Electronegativity. What are the periodic trends for each? So first of all, we need to describe the difference between the ionization energy and the electronegativity, which I will abbreviate. So ionization energy and electronegativity. So ionization energy is the energy needed to pull off electrons from an element. We can talk about first ionization energy or second ionization energy. So the first one is dealing with how much energy is needed to pull the first electron off an element. Okay, and then electronegativity is the element's ability to attract electrons towards itself. Okay, so how much it pulls electrons towards itself. And then what are the periodic trends for each? So for ionization energy, you're going to find that as you go to the right. Okay, and as you go up, you're going to have an increase in ionization energy and in electronegativity. What is the Lewis structure of hydrogen carbonate, or the bicarbonate ion? What is the electron pair geometry, molecular pair geometry, and hybridization of the central atom? So the hydrogen carbonate ion has chemical formula HCO3 negative. Alright, and we need to write its Lewis structure first before we can determine geometries. So this has a number of valence electrons of 1 from hydrogen, plus 4 from carbon, plus 3 times 6 from oxygen, plus 1 from the negative 1 charge. This is 24 valence electrons. Next, we're going to write our skeletal structure, so central atom connected to the outer atoms. So we're going to have the carbon attached to these 3 oxygens, and we're going to attach the hydrogen to one of the oxygens. With 4 bonds, we just used 8 valence electrons, so we have 16 more left. We'll put these on the outer atoms first. So 6, 12, 14, 16. Right, and now we have no more to draw. Now we're going to check the octets. So these hydrogens are fine. They have their 3 bonds plus their 1 bond, so that's going to be 8 valence electrons. Next we have this oxygen, which is fine because it has those 2 shared pairs and 2 lone pairs, and the hydrogen is fine because it only makes 1 bond. But the carbon is not fine. It only made 3 bonds, which is 6 valence electrons instead of 8. And we know that carbon really follows the octet rule. So what we need to do is make a double bond from either this or this oxygen. So we can do the one from the left. These electrons will transfer over, making a double bond. So whether you make the double bond from here or here doesn't matter. Now we are ready to answer questions about the geometry. So first, the electron pair geometry is about how many groups are around the central atom. So remember, carbon is our central atom, and there are 3 groups around it, and no lone pairs. So 3 groups around it is the trigonoplanar electron pair geometry. With no lone pairs around carbon, the molecular geometry is also called trigonoplanar. Finally, the hybridization is also dealing with how many groups the central atom has. And that is going to be sp2 for 3 groups around the central atom. Write resonance structures for the nitrite ion. So nitrite is written as NO2, and we need to write resonance structures for this. So this is about drawing Lewis structures and seeing if there are any alternatives to writing that same Lewis structure. Alright, so let's count the valence electrons. So there are 5 from nitrogen, plus 12 from 2 oxygens, plus 1. This is 18 valence electrons. Now we're going to write the skeletal structure. So N in the center, and surrounded by these 2 oxygen atoms. So we just use 4 valence electrons, and the other ones are going to go in the outer atoms first. And we just drew 12 valence electrons, and then we have 2 more left, so we'll place those on the central atom. So now we have no more valence electrons to draw. Now let's check the octets for this. So these oxygens are fine, they have their 3 lone pairs and 1 bond. But this nitrogen only has 6, because it has 2 bonds and 1 lone pair. So we need to make a double bond. Let's do the one on the left. So these electrons are going to go in transfer, making a double bond, now shared between the 2 atoms. Right, and then that completes the octet for nitrogen. Now notice that the double bond could have also come from the oxygen on the right, so there are resonance structures for this. Put them in brackets with their negative charge, indicating the charge of the compound, and then write a double-headed arrow between the resonance structures. And the other structure could have gone as this, so the double bond coming from the right, and still with a negative 1 charge. Okay, so these are going to be the 2 resonance structures for the nitrite ion. And the final one would be a hybrid between these 2. So it'd probably be something like, these connected to a single bond, definitely, but then partial bonds on both sides. So not a complete bond, and not totally absent, just a mix. For each atom in the structure below, find the formal charge. Next we have part B that says how many sigma and pi bonds are there, and C, how many lone pairs are there, and how many shared pairs are there. As mentioned in the last video, formal charge, I like to use the shortcut of saying it is equal to the number of valence electrons minus the number of dots minus the number of lines. Let's do carbon first. So carbon has 4 valence electrons minus the number of lines and dots. Well, it has 2 dots and it has 3 lines. So this is a negative 1 charge. For nitrogen, well, nitrogen has 5 valence electrons, it has 2 dots, and it has 3 lines. Nitrogen has a 0 formal charge. How many sigma and pi bonds are there? So 1 sigma bond and 2 pi bonds. Part C says how many lone pairs are there and how many shared pairs are there? Well, we see these 2 lone pairs. Okay, so 2 lone pairs. And how many shared pairs? Well, we see 3 shared pairs. Is this molecule polar or nonpolar? C, CO4. And we have some electronegativity values over here for the chlorine and the carbon atoms. So let's draw the Lewis structure for this. So it's going to look like C in the middle, Cl on both sides, and Cl is going to have all these valence electrons around it. As practice, you can go ahead and draw this structure on your own and see if you get the same thing. And you can comment down below if you'd like. Alright, so this is the structure for CCl4, carbon tetrachloride. Now let's look at these electronegativity values. So chlorine has a electronegativity value of 3.16, and carbon has one of 2.55. Clearly, chlorine has the higher electronegativity value, which means that electrons is going to be towards chlorines. Okay, so over here, we can write these as dipole moments. So as we know, this is a tetrahedral geometry, okay, in 3D. You can't forget that. Right, so basically one going back and one going forward, and these line into place. So what we are looking at here is that the bond angle between these chlorines, all of them, are equal. Okay, that bond angle is actually 109.5 degrees, and so this molecule has symmetry. So even though we would classify these bonds, right, as polar, the molecule in its entirety is nonpolar because all of these spoles are going outwards and they're symmetrical, so they're basically opposing each other.